When we're studying first-order differential equations, we'll often study these approximation techniques like slope fields or Euler's method, which will approximate the solution to a differential equation. But we don't talk often enough about how good they are, right? We don't talk about how accurate these approximations are. Sometimes we'll briefly mention it, but we don't usually back it up with data at the very least. So in this video, I'm just going to show you a very short, simple example and actually show you some data so that you can kind of get a feel for how accurate Euler's method is. Now, the point of this video is not to do an Euler's method example, so I'm going to fast forward through a lot of the algebra. The point is to simply show you how good these approximations are. So let's say this is our first order differential equation, dy dx equals y. It's a very small one. And our initial condition is that y of 0 needs to be 1. So the xy initial condition is 0, 1. All right, so let me set everything up here. So for this particular problem, I'm going to choose a step size of 0.2. If you wanted to come back behind me and redo this example with a step size of 0.1, it would be even more accurate, because as you make the step size smaller, you're getting finer and finer approximations. So this is about as bad as it gets. I'm kind of doing a worst case scenario here, because I wouldn't want anybody to watch the video and say, oh, well, Devin, you picked a really small step size. That's why your answers were so accurate. Now this is quite a large step size. Usually our step size is usually like 0.1 or even 0.05 or even 0.01. But nevertheless, here we go. Here's our x, y column. I'll show you why in a minute, why I have this bar stretched so long. We're going to add in some extra stuff in a moment. But the x coordinates, if our step size is 0.2, it would start at 0, and then it would increase by 0.2. So we'd have 0.2, 0.4, 0.6, 0.8, etc. So here's our x's, and we'll just kind of stop at 0.8. You could keep going if you wanted to. Now we have to generate the y coordinates. And to do that, we're going to use Euler's method. And if you recall from the last video, Euler's method is done this way. The newest y value is equal to the oldest y value, the previous y value rather, plus the step size times the differential equation evaluated at the previous xy point, right? So at the last xy point. So here's our differential equation. This guy is going to be little f of x comma y. So we'll remember that. And we've got our initial condition here of 1. And so here I kind of fast forwarded through all that algebra, but using that Euler's method, I got a list of these points, okay? So if you wanted to go more slowly and generate these, you're welcome to. It'll be good extra practice for you. All right, so this is what we get from Euler's method, but how good is that? We have no idea. I have no idea if this is a great approximation to the solution curve or a terrible approximation. We have no idea. Well, that's going to be kind of the emphasis of what we're going to talk about. See, this simple differential equation right here, I actually know what his answer is. And just think about it for a moment. What function, if you took its derivative, would be the same as the original function? Think through all the functions you know, sine, cosine, tangent, all those guys. Well, you probably could have cheated a little bit. I've got it on the screen right here. The actual answer is e to the x. That's the guy whose derivative equals himself. The derivative for e to the x is e to the x, as we well know. What about the initial condition? What is e of 0? Well, e of 0 is 1. So it even satisfies the initial condition. So this is what you would call the perfect answer. This is perfect. There's no error involved at all in this guy. These are approximations. This is the perfect solution right here. So here's what we're going to do. We're going to make up another column where we're going to plug in these x values into the solution function, and this is what these y values either should have been or should have been close to. Right? So these are not going to hit dead on, but they will be very, very close. And this will give you an idea of how accurate these answers actually were. So e to the 0 is 1. Now that's a perfect match. That matches perfectly. Now why is there no error there? Well, this was the initial condition. We can at least get the initial condition right. The error starts beyond the initial condition. Now what's e to the 0.2? E to the 0.2. That's 1.221. You can do it on your calculator. Look how fantastic this approximation is. These are practically the same. It's got a difference of 2/100ths of a unit. It's very, very small. So hopefully that convinces you that that our Euler's method worked extremely well. These are extremely close together. My y value was almost identical to the actual y value that it should have been. All right, let's keep going. E to the 0.4 is 1.492. You can do that on your calculator. A little bit farther away is 5/100ths of a unit away. Is farther than 2/100ths of a unit away. Why is it getting worse? Well, to be honest with you, it's because we're leaving the initial condition. There does start to become greater error as we leave the initial condition. E to the 0.6 is 1.822. E to the 0.8 is 2.226. So those are the exact y values that Euler's method should have approximated. So in closing, let's make another column that looks at the error. Here's the error. First of all, there's no error at the initial condition. There's a little bit at 0.2, a little bit more at 0.4, and 0.6 and 0.8. So you see the error does start to grow, but I hope you'll kind of take to heart the fact that Euler's method does a great job. It does a fantastic job in approximating the actual y values that it should have gotten, even though there's a little bit of error involved.